Welcome back to another video on linear motion. In this video we're going to talk about how do we actually model motion with graphically. So we're going to talk about motion dot diagrams and position versus time graphs for specifically objects with constant velocity. So let's go to the track. If we actually could meet in person, we would go to the track. But let's pretend that we're looking like top down on the track and we have runner A and runner B, and we've established a reference frame where runner A is at horizontal position 0 and runner B is starting at 100 meters, horizontal position 100 meters. Okay? And they run, and we're taking like snapshots from above, like in our drone, every 1 second. Okay? So their motion would appear like this. Let's say runner A is wearing a red hat, runner B is wearing a pink hat. Okay, so this particular way to model motion is called a dot diagram. So these dots are taken at equal time intervals, and as you can see, the blue dots are further apart, and therefore the runner was going faster. Runner B, they're closer together, which means that in each time interval, like there was a smaller change in position on each time interval. So the distance between the dots matters. And before you compare dot diagrams, you do have to know if the time intervals are the same between each dot. But here we see that runner A is traveling faster, runner B is traveling in the opposite direction and slower. And with the dot diagrams, you have to pay attention to the time that's shown to tell the direction. So we can tell that the time increases to the left with runner B, I guess for you is to the left with runner B, and to the right for runner A. So that tells you what direction they're going. The last thing we can see from this motion dot diagram, if there's equal spacing between the dots, then they had an equal amount of position change for each time interval, which means their velocity is constant. Okay, so these are useful, and you may be asked to interpret them, but what becomes more useful is to actually graph the position as a function of time. So we can kind of think about like turning that dot diagram on its side, and then instead of just plotting the actual position and labeling the time points, we're going to plot that position as a function of time. Okay, so every second we have the position changing, and what we get is a horizontal, or not horizontal line, what we get is a straight line. Okay, and that's because the velocity is constant. So we get this straight line here. And we know from math that slope equals rise over run. Okay, so there's an interesting relationship here that occurs, is that the slope, because our position is on the y-axis, that's the rise, and our time is on the x-axis, that's the run in math terms, we get delta x over delta t, which we have defined as velocity. So it ends up that the slope of a position versus time graph for an object in motion will be the velocity of that object. And here, when we're at constant velocity, it's pretty easy to just determine the slope. If we're not at constant velocity, it's still that relationship that the slope is the velocity is still true, but we have to look at like instantaneous velocity and determine this slope at a particular time point. Okay, so for right now, let's figure out the slope of this line here, so we can determine the runner A's velocity. So we have 104 minus 0, that gives us our rise, our delta x is 104 meters, and that took a time of 14 seconds, so 14 minus 0 equals to 14. So our velocity is 7.4 meters per second for this runner. And so just writing it down, that's important. The velocity of an object in 1D motion is the slope of an x versus t graph. Okay, so this is for linear motion. We know the velocity from the slope of the position versus time graph. Okay, let's look at runner B. Runner B's graph is going to look a little bit different. We're doing the same thing. We're going to plot the position versus time, but remember runner B started in our reference frame at 100 meters. So as we start running here, and runner B is now going to, well, on the dot diagram, right, it was to the left on your screen. But in this case, the slope appears to be negative. And so when we look at our line that's created, because that's constant velocity, we have a slope. Our rise is negative 90 meters over 20 seconds is our run. And so our velocity ends up being negative 90 over 14, or negative 4.5 meters per second. So remember, velocities, they have that positive or negative sign matters. This tells us that the runner was going in the negative direction in our reference frame, which we did indeed see with the motion dot diagram. Okay, so let's take our equation for average velocity and kind of come up with a general equation for constant velocity linear motion. Okay, specifically for constant velocity. So let's kind of simplify things here. Let's turn this Vx average kind of cumbersome variable that we've been using and just turn it into a Vx. Let's say that we're going to always just have our x final as x and say that t final is t. And we saw in a lot of these examples that the initial time and initial position, or that our initial time was 0. So let's keep our initial position as x naught, but let's turn our t naught into just 0. So we get this equation that Vx equals x minus x naught over t. Okay, if we multiply both sides by t, we get an equation that says Vx times t equals our displacement. And let's add x naught to both sides to get an equation that solves for our position as a function of time. So this will be useful for any constant velocity linear motion problem that you do. You can calculate the position of the object by taking its initial position and adding to that Vx times t. So the velocity of the object times t. And remember, this works for constant velocity problems. So if your velocity is changing, things get a little bit different. But if you have a constant velocity, this equation can be used to solve for the position as a function of time. So here is what all our variables mean. I'll let you read that. I don't need to read it to you. You can pause, write it down in your notes. And the important thing to start this one with is that this only works for constant velocity linear motion. Okay, so your velocity has to be constant for this to work. Okay, that's all I got for this video. Thanks for watching.